Before jumping into planar systems, we consider the ordinary differential equation. dx dt equals a constant, times x, or x prime equals ax, and a is any real number. Now if k is a real number, then the function x of t, a solution to this differential equation, is equal to k e to the a t. We can show this by differentiating this, and we get a k e to the a t power, which is a times x. Next, we would like to show that this solution is the only solution by letting u of t be another solution, so that it satisfies the differential equation u prime equals au. Now, if we compute the derivative of u of t multiplied by e to the negative at, what we wind up finding out is that from the product rule, differentiating with respect to time, we get this expression which is going to equal 0. What does that imply? It implies that u of t times e to the negative at is a constant, or we'll just call that constant k, and therefore u of t is equal to k e to the at, which is x of t. This shows that there are no other solutions. Now, by specifying some initial conditions, one can determine the constants. And by determining the constants from those initial conditions, we generate something called a particular solution. For instance, consider x of t naught equal to u naught. Then we get the value of k equal to u naught times e to the negative a t naught. And therefore k e to the a t naught power is equal to u naught. Now if we simplify this by letting t naught equal 0, x of 0 will be u naught, which is just going to be the value of k. However, if k is 0, then x of t is also 0, and this would be considered a constant solution. Constant solutions are also called equilibrium solutions. So therefore, for this differential equation, in this case, we'll call a, in the differential equation x prime equals ax, a parameter. And so the value of a determines the nature of the solution. That is, do we get exponential growth or do we get exponential decay? What kind of behavior do we observe as we vary the parameter a? Well, first, if we observe that if a is a positive number, then in our solution, as t goes to infinity, so does our exponential, and therefore its growth. If a is equal to 0, then k is a constant. X of t is a constant. And if a is less than 0 or negative, then our solution will tend towards 0 like exponential decay does. Therefore, the qualitative behavior of the solutions can be understood and described by looking at the parameter of a and different values for a. Now, when an equilibrium point tends towards infinity as time goes on, we call it a source. On the other hand, if an equilibrium point tends towards 0, we call that equilibrium point a sink. Now, to better visualize these equilibrium points and solutions to differential equations, we turn towards a slope field. A field of many tangent vectors that point in the direction of the solutions. It's a powerful tool for analyzing differential equations. Like little magnetic poles, these tiny tangent vectors guide a particle which is on a solution curve path through the field of moving parts. When the arrows point in a certain direction, we get a certain solution type. Notice for constant solutions, we get straight line solutions and all the vectors point in the same direction. Now, if we pick a particular value, say point P, we get a particular curve. The initial condition gives us a particular solution. And for different initial conditions, we get a family of curves described in general by the slope field. And the slope field is basically describing the general solution to the differential equation. So by varying the parameters of A, we also alter the vector field associated with our differential equation, and therefore our solution curves as well. And thus they'll take on exponential forms for A positive. And if we vary our parameter in the negative direction, we'll then see the growth turn to decay. At 0, we still have these constants, but here, if the A is negative, we get exponential decay. So the different values of A gives us different families of curves, and different initial conditions have particular curves within that family. Now we'll consider what happens to a planar system of differential equations. Consider x double prime plus px prime plus qx equals 0 as second order differential equation. By letting y equal x prime, we can turn it into a first order differential equation, y prime plus py plus qx equals 0, and then write it out as a system of differential equations, x prime equals y, and y prime equals negative qx minus py. Now this system of differential equations generates a matrix equation. And this matrix equation takes on a familiar form, x prime equals ax. Only this time the matrix A has 4 components, 4 coefficients, a, b, c, and d. Here we want the determinant to not equal 0. Now, from this matrix, we can determine its eigenvalues given by lambda 1 and lambda 2, and associated to those eigenvalues are eigenvectors, v1 and v2. These eigenvalues will play the new role of our parameters. Before we had a single number a. Here we have 4 numbers to play with, and the eigenvalues that are generated from those 4 numbers, lambda 1 and lambda 2, those eigenvalues, they are the parameters, and they will make a landscape for us in something called the phase portrait, allowing us to look at the behavior of this planar system. So, phase portraits for planar systems, considering again x prime equals ax and this matrix A given by a, b, c, and d, we're first going to start off with real distinct eigenvalues. So we're going to let lambda 1 and lambda 2 be real numbers and distinct, not the same numbers. And we'll consider that lambda 1 will be less than lambda 2. This breaks up into a few cases. 1. Maybe lambda 1 is negative and lambda 2 is positive. Or maybe both lambda 1 and lambda 2 are negative, or the third case, both lambda 1 and lambda 2 are both positive. But in all those cases, lambda 1 is less than lambda 2. Alright, so time for an example. Consider this matrix, a very straightforward and simple matrix, where lambda 1 is negative and lambda 2 is positive. This gives us 2 very simple, straightforward differential equations. And solving for the eigenvalues here, lambda 1 and lambda 2, the numbers along those diagonal, is going to be the eigenvalues for our matrix, and they generate the eigenvectors, which are the standard normal unit vector bases. Now the one that's along the x-axis is the eigenvalue associated to the negative, and therefore all the solutions along the x-axis will tend towards 0, whereas the positive eigenvalue will give us a solution along the y-axis here that will tend towards infinity, because it's a positive eigenvalue. So negative eigenvalues tend towards 0, and we say that that's a stable line, where the ones that tend towards infinity is an unstable line. So the eigenvectors point in the direction that our solutions will go, and here we get what's called a phase portrait saddle. So in one direction it increases, where another it decreases. Let's consider a second example, such as the matrix A equal to 1, 3, 1, negative 1. This one will generate the eigenvalues plus or minus 2 and the eigenvectors 3, 1, and 1, negative 1. So one solution will be the unstable solution, the one with the positive eigenvalue, and the one with the negative eigenvalue will be the stable solution, and that'll be along the vector 1, negative 1. These two solutions together as a linear combination will form our general solution, and alpha and beta would be constants determined by some initial conditions. So if we specify some initial conditions, we can define what alpha and beta are and get a particular solution. One notices that this is also a saddle phase portrait, but the vectors are no longer along the x and y axis directions. Alright, so let's consider the case where the eigenvalues are both negative. Given the matrix of the form again, lambda 1, 0, 0, lambda 2. X of t equals alpha e to the lambda 1t times the vector 1, 0 plus beta e to the lambda 2t along the vector 0, 1. In this particular case, both eigenvalues are negative, so therefore both of those solutions will tend to 0 as time goes to infinity. Along the straight line solutions, we see our phase portrait gives us something that we will give a specific name to because of all the solutions going to 0. One thing we can note is that lambda 1 is called the stronger eigenvalue, where lambda 2 is the weaker eigenvalue, and solutions will tend to hug the straight line solutions that are associated with the weaker of the eigenvalues. So here the weaker of the eigenvalues is along the y-axis. Therefore the solutions hug that straight line solution in our phase portrait. This is known as a sink because everything is going to the origin, sort of like a drain in a sink. Alright, up next, consider if we have the matrix, again, lambda 1, 0, 0, lambda 2. And in this case, both eigenvalues being positive would yield a source where all of the solutions tend away from the origin towards infinity. Quite the opposite of the last situation we just saw. So then we have to consider the case of what happens when we get complex eigenvalues. So when a matrix A has complex eigenvalues, we no longer have straight line solutions. The phase portrait associated with complex eigenvalues we'll start with is called the center. And the matrix usually takes on the form 0 beta, negative beta, 0, where beta is not equal to 0. This gives us the characteristic equation lambda squared plus beta squared equals 0, and lambda is equal to plus or minus I beta. I being the square root of -1, the imaginary unit. So we take the positive eigenvalue, I beta, and its associated eigenvector, 1i. That gives us the general solution, x of t is equal to e to the I beta t times 1i. That's our complex solution to our differential matrix equation. What we'll do here is we'll multiply through first with that exponential, and then we'll use Euler's formula to expand out e to the I beta t into its cosine and sine parts, or otherwise known as its real and imaginary parts. Now when we break it down into its real and imaginary parts, we can also break the vector up into its real and imaginary parts, yet the vectors themselves are real vectors, and therefore we can generally form a solution based on the form of this. So we'll have what we'll call a real solution and an imaginary solution. But the imaginary solution is just associated with the imaginary part of our complex solution. So now what happens if we let t equals 0 in our real solution? We get, well, in both the real and imaginary parts, we get the standard normal unit vectors. And therefore we can write the general solution to our system as x of t is a constant times our real solution plus another constant times our imaginary solution, where c1 and c2 will be determined by our initial value problem, our initial conditions. Here's the phase portrait associated with such a solution, and you can see why it's called a center, because the solution curves are concentric circles. Now next we're going to consider what it looks like for a phase portrait that's called either a spiral sink or a spiral source. And this starts off with a matrix of the form alpha beta negative beta alpha, where alpha and beta are both non-zero. The characteristic polynomial equation yields the eigenvalues alpha plus or minus I beta. Next, we would determine the eigenvector associated with lambda equal to alpha plus I beta, and that vector is 1i. Therefore, we have the complex solution x of t equals e raised to the alpha I beta times t times the vector 1i. And breaking it up into its real and imaginary parts, we see that the general solution has coefficients of e to the alpha t, which turns our straight line solutions into curved spirals. So the general solution is of the form x of t equals a constant times e alpha to the t, and then this vector, plus c2 e to the alpha t times this vector, the imaginary and real parts that we had talked about earlier. And again, these factors of e to the alpha t are what convert our straight line solutions from before into spiral-like solutions. So our phase portraits are determined by the alpha part. When alpha is negative, the curves spiral into the origin. We would call it a spiral sink. And then alpha being positive, the curves spiral away from the origin, like exponential growth, a spiral source. We also must consider what happens with repeated eigenvalues. So let A be the matrix, lambda 0, 0, lambda, a lambda being the repeated eigenvalue. Every non-zero vector then becomes an eigenvector, since it satisfies the equation AV equals lambda V for any vector in R2. So solutions are therefore of the form x of t equals alpha e to the lambda t times that vector, times a vector. So each solution lies on a straight line through the origin along the direction of that particular vector, and it'll either tend towards 0 or tend away from 0 to infinity. And that'll depend on the nature of the eigenvalue. A more interesting case is if we alter the matrix A just slightly by making it lambda 1, 0, lambda, and the two eigenvectors being again repeated. For this particular solution, we actually only have one linearly independent vector, 1, 0. And hence, since we only have one straight line solution, taking of the form x of t equals alpha e to the lambda t times 1, 0. To find any other solutions, the first thing that we note is x prime is of the form lambda x plus y, and y prime is lambda y. If y is not 0, then y of t takes on the form beta e to the lambda t. Therefore, we get x prime is equal to lambda x plus beta e to the lambda t. This is a non-autonomous first-order differential equation. In other words, it depends on time. So one would want to guess a type of solution to try out and see if it works to generate, say, a particular solution. So if, let's say, we guess x of t is equal to alpha e to the lambda t plus a constant mu t e to the lambda t power, like a derivative, then we try this and substitute it into our formula, and it turns out that this is in fact the general solution. You see, the matrices that we've been working with, they're called matrices in canonical form. So we had matrices such as the following. Canonical forms allow us to find straight line solutions. And now any linear system can be brought into canonical form. And we do this with a change of coordinates. You see, many planar systems may be brought into canonical form under a linear transformation. Now recall that a linear map, or a linear transformation, on R2, well, it's a function, and it goes from R2 to R2. And it takes on the form of a matrix times a vector xy, and it produces a new vector, ax plus by, cx plus dy. So the map, or the matrix T, is the linear transformation, and suppose that T is invertible, therefore it means it has an inverse. Its determinant is not equal to 0. Then let the matrix S be its inverse. So when we compose T with its inverse, in either order, it produces the identity matrix. So if we're working with a 2x2 system, the 2x2 identity matrix. Finding a 2 by 2 inverse matrix is not terribly difficult to compute. Now, if T is invertible, we say T is invertible if and only if its determinant is not equal to 0. And so, consider instead of x prime equals ax, consider a different system. Consider y prime equals t inverse at times y, and T is some invertible map. Now, why would this combination of matrices work in our favor? Well, let's first observe that if y of t is a solution to this new system of equations, then x of t equal to our map t times the solution y solves our differential equation x prime equals ax. And just to show this, we'll do a little substitution. And this is where that form of the matrix that looked really weird to begin with now shows its usefulness. When we start multiplying things through, we get t times its inverse, which gives us an identity matrix on many sides of our calculation. And thus, when we work this down, x prime is equal to the matrix A times ty. Therefore, the linear map converts solutions of y prime into solutions of x prime. You see, that linear map takes something and turns it from canonical form to non-canonical form and backwards. So when we want to find straight line solutions to a differential planar system that is not in canonical form, we can diagonalize it and put it into canonical form. So let's say our goal is to find a linear map that converts a given linear system into a canonical form. Alright, let's start with some real eigenvalues that are distinct, not equal to each other. And they have associated with them their eigenvectors, v1 and v2. Let's take those eigenvectors and create the columns for our matrix T. If we apply our linear map to a standard basis vector E sub j, we get our eigenvector Vj. And also, if we apply the inverse map T inverse to Vj, we get the standard vector basis Ej back. So if we compose the matrix T inverse AT and apply it to the basis vector Ej, we see that it produces the eigenvalue lambda j times the basis vector Ej. So therefore, T inverse AT assumes the canonical form where our eigenvalues are along the diagonal and the other entries are 0. Real and distinct eigenvalues take on that canonical form. Suppose we have complex eigenvalues. Right, those were the ones of the form alpha plus or minus I beta, where beta was not equal to 0. The goal was to find a set of vectors, perhaps linearly independent vectors v1 and v2, which are the real and the imaginary part vectors of our solution. So now, if the vectors were linearly dependent, v1 would be a multiple of v2. Right, so if we want them to be linearly independent, right, we can't have that happen. Now going through the calculation to see what this would imply, A times V1 plus IV2 gives us C plus I times A V2. In other words, there's a contradiction. The left-hand side is a real vector, where the right-hand side is an imaginary vector. So therefore, V1 and V2 would have to be linearly independent. So that since V1 plus IV2 is an eigenvector associated with the lambda alpha plus I beta, we have A times V1 plus IV2 equals alpha plus I beta times V1 plus IV2. And that sets up a system of two equations. And if we let, again, our linear map be made up of the vectors, the column vectors for V1 and V2, we can then put our matrix into canonical form by calculating T inverse AT. And just going through and showing you by doing this in the canonical form for E1 and E2, the basis vectors, we get the canonical form alpha beta negative beta alpha. So hopefully you're putting together that the matrix itself, the linear map, really is the determining factor for the way that our phase portrait is going to come out. Let's consider another harmonic oscillator. X double prime plus 4x equals 0. That gives us the matrix 0, 1, negative 4, 0. Lambda squared plus 4 equals 0 gives us lambda equals plus or minus 2i. So we have some complex eigenvalues here. Taking the positive eigenvalue 2i and calculating the eigenvector associated with that, we get 1 and 2i. So a complex solution that we may write down for this system, e to the 2it times the vector 1, 2i. Separating into its real and imaginary parts, we can get our real and complex, or real and imaginary vector parts that we can put into, and that we also see our pi periodic, given the nature of their arguments. So now let us take T to be the matrix whose columns are composed of the real and imaginary vectors that we found. So we have 1 and 2i, and we have real and imaginary parts for that. So then we get the matrix T equals 1, 0, 0, 2. We easily compute T inverse AT to be 0, 2, negative 2, 0. And that is in canonical form. So these phase portraits, they show that T maps that circular center solution to elliptical solutions, circles that have been stretched in a certain direction. So we're going to come to the heart of the matter of why phase portraits are so important to planar systems. It is because the phase portraits themselves can help us classify planar systems into certain categories. And this is going to be done by creating something called the trace-determinant plane. For a matrix A given with the coefficients A, B, C, and D, the characteristic equation comes out to be lambda minus A plus D lambda plus AD minus BC equals 0. Now part of that you might recognize, the AD minus BC. But take a look at the coefficient of lambda, A plus D. That's known as the trace of the matrix A. It's the sum of the diagonal elements. And the AD minus BC, you guessed it, that was the determinant of the matrix A. So the characteristic equation is really lambda squared minus the trace of A, lambda, plus the determinant of A equals 0. And using the quadratic formula, we can generate the eigenvalues to be 1/2 the quantity trace A plus or minus the square root of the trace squared minus 4 times the determinant. So that gives us a lot of predictability power if we know both the trace and the determinant of our matrix A. Notice again that the trace is the sum of the roots of the characteristic equation, and the determinant is really the product of the roots of the characteristic equation. Let's use a curly T for trace and a curly D for determinant so that we can write this in a little bit more simplistic form. So by knowing T and D, that tells us the eigenvalues of A, and therefore everything that we need to know about the geometry of our solutions. Our planar differential system of equations can be classified into its phase portraits based on T and D, based on the trace and the determinant. So therefore we will construct the trace-determinant plane, where T and D will take on coordinate values, and based on those coordinate values, we will get a certain type of phase portrait. And you can see that the discriminant, t squared minus 4d, yields the nature of the solutions. T squared equals 4d is this parabola that separates the regions along with the plane for the determinant and trace, and here the different eigenvalues will determine the different the different discriminants, t squared minus 4d, in the quadratic formula, which determines the solutions in this plane. And so we can see that it's broken up into several pieces. The location of the coordinate TD relative to the parabola given by t squared minus 4d equals 0. It tells us everything that we need to know about the nature of the general solution to a system, a planar system of differential equations. The trace-determinant plane is one that shows us when different values of t, perhaps if t is negative or if t is positive, we are above the trace line. Now for a trace equal to 0, we get a center. And also if we examine what happens when the determinant is, negative, and when the determinant is equal to 0, and when the determinant is positive. We get that saddle situation when the determinant is equal to something that is negative. And therefore it is on the bottom portion of our trace-determinant plane. When the determinant is greater than 0, but the trace is less than 0, we get a real sink. And in the case of the determinant and trace both being positive, we get a real source. Math is more than just equations. It's a gallery of artwork. And I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.